Previously we saw that in order to have power amplification or power gain, we need to have a nonlinear circuit, and we also need an additional source, because every element is passive. If you just have a single source which delivers the signal power, then what comes out, the power that comes out is going to be smaller than the input signal power. So we need to have a nonlinear device as well as two sources. One is the source which provides the desired signal, and also another is a sort of a power supply. Okay, usually it's a DC source. Okay, and somehow some of the power that is taken from the DC source will be converted to useful form in the form of the signal. Okay, so that's how we get power gain. Now before we can discuss amplifier devices, we have to learn how to analyze nonlinear circuits. Okay, because this is usually not what is taught in basic circuits classes. So we'll go step by step, and the analysis of nonlinear circuits is not as easy as linear circuits, but we can make some approximations and make some progress with analyzing nonlinear circuits. Okay. Now, eventually we want to have two-port elements, that is an element where you can provide an input from one side and take the output from the other side. But because we are yet unfamiliar with nonlinear circuits, we will first consider nonlinear one ports and then go to nonlinear two ports. But the general method of analysis shown with the nonlinear one port will also be applicable to nonlinear two ports. Okay. Now I will represent a general nonlinear one port like this. If it has a voltage V across it, it has a certain current I through it, and I will be some function of V where this F is nonlinear. Okay. Now of course in case of a resistor which is linear, we have a similar relationship where I is G times V, where G is the conductance. So the single number conductance describes the resistor, and in case of a nonlinear element, the function f describes the nonlinear element. Okay. Now of course we can talk in abstract terms about a general nonlinear element, but it's also useful to learn about a very frequently used one port nonlinear element, which is a diode. Okay. So if the voltage across this is Vd, the current ID through it will be given by some nonlinear function. Okay, I am going to show that in a moment, but one thing I have to show is the diode is represented by a symbol like this, and it is asymmetrical. Okay, so this side is known as the anode or the plus terminal, and that side is the cathode. And while describing the characteristics, this Vd is defined with the anode being positive, and ID is defined with the current going into the anode. Okay, so that's the usual passive sign convention. Okay, so with this polarity, this ID will be Is exponential Vd divided by Vt minus 1. Okay. Now this Is is called the saturation current. Okay, it's some property of the diode. It is somewhat similar to the conductance of the resistor. Okay, so you can have resistors with different conductances. Similarly, you can have diodes with different saturation currents, and the saturation currents can vary widely, just like you can have a 1 ohm resistor or a 1 mega ohm resistor. But I'll just give you some value which you can find. This Is itself will be a very small number, 10 to the minus 15 amperes, let's say. Okay. And there is another constant here, which is Vt, and this is not really a property of the diode, but it's a fundamental constant. and it is given by Kt by Q, where K is Boltzmann's constant. You would be familiar with this, and T is absolute temperature, okay, and Q of course is the electron charge, okay, and this number Kt by Q, this is known as the thermal voltage. Obviously it has dimensions of volts, and you see that it must be like that to balance the dimensions here, because Vd is volts, Vt also has to be in volts, so that the argument of exponential is dimensionless, okay. Now of course this is something that is directly proportional to the absolute temperature, and it turns out that at room temperature this Vt is Kt by Q, and it's equal to 25.9 millivolts, and we will frequently approximate it with just 25 millivolts, okay. So this is a number worthwhile remembering. The thermal voltage Vt is 25 millivolts at room temperature, okay. So sometimes it's approximated to 26, or sometimes you use 25.9, but this is good enough, 25 millivolts, okay. So now let's see what this characteristic looks like. As usual, as for any element, we can also graphically depict the characteristic Id versus Vd, and we said Id is this Is exponential Vd by Vt minus 1, okay. It's some nonlinear curve, but we can see how it behaves. So first of all, when Vd is very negative, that is Vd by Vt is a large negative number, this exponential of a large negative number is close to 0. Of course, it will never be exactly 0, but it will be very small. So in this parenthesis you will just have minus 1. So Id will be approximately minus Is when minus Vd, that is the negative value of Vd, is much more than Vt, okay. So what I am saying here is Vd is large and negative, okay. So Id approximately minus Is, it means that Id will be something like this, okay, when Vd is large and negative, and this number is minus Is. So what it means is, in this region when Vd is negative, by the way, that region is called reverse bias, the current will be almost constant and it will be equal to minus Is, and in fact this is the reason why Is is called the saturation current or the reverse saturation current, okay. Now when Vd equals 0, okay, this number is 1 and Id will be equal to 0. So that means that this Id will be 0 when Vd is 0, okay. And as Vd becomes positive, this exponential grows rapidly with Vd and the current increases rather steeply, okay, something like that. So this region where Vd is greater than 0, significant currents can flow, and this is known as forward bias. Okay, and Vd less than 0. The current is very small. We saw that. I gave you a typical value of Is, which is 10 to the minus 15 amperes. Okay, so it is very small, and more than the absolute value of that, the significant thing is that when Vd is more than 0, the current is much more than when Vd is less than 0. Okay. So when we say small and large currents, we have to relate it to something. What we mean is that the reverse bias currents are much smaller than forward bias currents. Okay. This is reverse bias. Okay. And for Vd equal to 0, Id will be equal to 0. Okay. In fact, this is a condition that is necessary for passivity. We of course know that a resistor's characteristic would look like this, right? It will be a straight line passing through the origin, and it will have a slope of conductance or the reciprocal of resistance, and it is passive. Now, you must know this from your basic electrical circuits courses. If the IV characteristic of a one port or a two terminal element is in the first or third quadrant, it is dissipating power, because V times I is positive. Here in the first quadrant, both V and I are positive. In the third quadrant, both V and I are negative. So in both of these, it will be dissipating power. And in these quadrants, second and fourth quadrants, V times I will be negative and the element will be generating power. So if you have a passive element, it cannot have any part of its characteristic in either the second or fourth quadrants. Okay. So passive element means the characteristic only in first and third quadrants, and this of course implies that it has to pass through the origin. Okay. So now this is for a diode, and in summary, diode has a very small current in reverse bias, that is when the diode voltage is smaller than 0, and note that the diode voltage is defined with a specific polarity and the symbol of the diode is asymmetrical. So please keep that in mind while figuring out forward and reverse bias. Okay. And when it's in forward bias, it can have significant currents. Now of course, the general nonlinear element can have arbitrary characteristics, but if it's a passive nonlinear element, it is going to have characteristics which are going to pass through the origin and be only in the first and third quadrants. It can be anything. Okay, some general f of v. Okay. So this is just an introduction to a two-terminal nonlinear element. Okay, and we have seen the characteristic. We can describe it with an expression or we can draw a graph.